Okay, so good evening, everyone. Welcome to the measure phase of the Lean Six Sigma Yellow Belt certification course. In this phase, we are going to quantify the pain point that you will be facing when you are running a Six Sigma project. So as a recap, we are following the course of this Lean Six Sigma Yellow Belt method course by following the Six Sigma DMAIC methodology. We have finished the define phase and we are now moving into the measure phase. In the define phase, we've looked at the tools that will help us identify the focus area of our project. In measure, we quantify the pain point. And part of this one as well is we'll get an idea of what the frequency of our defects is. So the measure module is we'll covering three main topics in the measure module. We will tackle the first part is about statistics background, and then there is a section on graphical tools, and the last part will be a concept called process capability, or how we describe a process. The measure module is math heavy. And for this session, we will only cover part one, which is the statistic background. And next week, we will cover the graphical tools and process capability. So we'll start first with statistics. So statistics is heavily used in Lean Six Sigma, okay? And some, or if not all of you, might have encountered this in college or in high school. As a recap, what is statistics? It's just basically the science that deals with the collection of data, classification, analysis, and interpretation of facts and data. It is the language that is used in Six Sigma to describe and analyze the physical variability of a process. So you might be asking, why statistics? Okay. Because statistics will help us make effective decisions. Okay. Although statistics is not enough, okay, so one needs to have a strong technical knowledge. So everyone has their own domain expertise, everyone has their own technical knowledge. But if you couple that with a good statistical skills, a good background on statistics, you should be an excellent problem solver or an excellent Lean Six Sigma practitioner. Okay. So let us imagine a scenario. So assuming you work in, let's say, a call center where you are handling customer calls and you're processing their, let's say, requests. And then you are expected to resolve the request, let's say, within a time frame. So they give you maybe some specific questions to fill out a form, and then you assist them, and then the call is finished. So let us imagine that is the scenario. That is your process. So each transaction, let's say, takes time, and you estimate that normally it would take you about 5 minutes to respond to a customer call. Okay, so you looked at the data in terms of the resolution time, which means from the time you answer the phone until you put it down again and resolve the customer issue. So let's say in one transaction, it took you 5.4 minutes. Maybe in the next transaction took you 5.1 minutes. And let's say the third transaction took you 5.8. Let's say the fourth one took you 6.2 minutes. At this point, will you be concerned, or would you feel that something is wrong with your process?
Yes.
Okay, so that's your answer. Yes. Let's continue. So it might be that this variation that you're encountering is probably just normal. Okay. So the next one took you 4.7 minutes, and the next one took you 5.5 minutes. So in this kind of process, actually, it might trigger you that there might be wrong, but it actually could be that it's just a normal variation of your process. So sometimes it will take you 5 minutes, a little over 6 minutes, or maybe sometimes could be less than 5 minutes. However, let's say you have another transaction that's probably 11.3 minutes. Then this is probably more likely that there might be a special cause that led this to have somewhat a different variation, a higher deviation from what you would normally expect from your process. Okay, so we're just looking here right now at your transaction time. And it might be that when you investigated this 11.3, you realize it took you longer because maybe the call was from a Spanish-speaking person, and you needed some time to translate what he was saying from Spanish to English, and that's probably the reason why it took you longer. And it might be in the case of 6.2 minutes, there's nothing really out of the ordinary. It's just probably another day where it took you a little bit longer, but there was nothing really extraordinary. So with these examples, we will cover what I call the principles of variation. Okay, variation. So everyday process, there is variation. So everything varies. Variation is the norm, not the exception. So as we've seen through that customer resolution example, we see that the time it will take us to process the transaction varies. Okay. And then all variations are actually costs. Some are obvious, while others are more obscure. Okay. So in the example we recently looked at, the 11.3, it was obvious when we investigated. It was because the caller was a Spanish speaking person and had a hard time speaking in English, so it took you longer because you had to translate. Whereas, let's say on the 6.2, you're not able to find any cause, so it could be that the cause was more obscure. Okay. So not all causes of variations are equally important. They follow the 80-20 rule, which means that probably 80% of the major variations in your process are probably just caused by 20% of the factors. And it's up to you to investigate what these critical few factors are. And we will cover this 80-20 rule in the next section of measure phase. Okay, so just hold that thought, the 80-20 rule. And causes of process variations can be categorized into one of the following groups. Okay, so in my experience, when we categorize the causes, it's a good rule of thumb to categorize this into these groups. Could be the cause could be man, it could be machine, it could be method, could be material, could be measurement, or it could be Mother Nature. Okay. Stable processes produce consistent patterns of variation over time. Okay. So stable processes, they have variation, but their variation is consistent. So which means that if something is consistent, although there is a variation, but if that variation is somewhat consistent, you are able to somewhat predict its performance in the future. And the variation in a stable process comes from common causes, which are inherently part of the normal process. However, there could be also variation that comes from special or assignable causes, okay, which can make your process become unstable or out of control. And these are unpredictable occurrences. Okay? So you probably would have to look at your process, and if you see that there is something that makes it quite out of the ordinary, then it could be due to a special or an assignable cause. And to understand the causes of variation, you might want to stratify your data in various sensible ways and compare. So let's say in the customer resolution times, you might want to study about the different times, and it turned out that when you studied it, the one that took longer time, the factor that affected it was about the language came about. Okay. So there is a variation, and one way that you can understand special causes of variation is to stratify your data. Okay. And actually, the major causes of a process variation can be discovered by analysis of the process and statistical tools. However, for yellow belt, we will not cover this statistical tools, the deep statistical tools that are able to help us study the cause of variation. This is more explored in the higher level, like the green belt. And reducing process variations is will help us produce lower cost and improve the quality of our process. Okay, so those are just some concepts on variation. Now, how do we measure variation? Okay, so here we have 3 charts. Okay, the one on the left is the raw data. Okay, if you present your data like this, it's hard to probably get meaningful information. And the next one is a graphical representation of the data that was shown in the raw data. And now this one is more visual. Okay, this is what you would call as a histogram. And a histogram can tell you about the frequency of a value that happens. So in this case, if you look at number 7, that one has probably the tallest bar, and that's because 7 is that chart is interpreted as 7 occurred 7 times, 8 occurred 5 times, and 9 occurred 3 times. So that's a histogram. And further on the rightmost is what we would call a distribution curve. A distribution curve is like the trend that would mimic the histogram that was shown. Okay, so if we have continuous data, the shape of the curve will be somewhat shown on the rightmost side. So how do we interpret that curve? Along the curve, it tells you how likely it is that value will be encountered. So let's say between 5 and 6, okay, so let's say this between 5 and 6, it means that a value between 5 and 6 is more likely to occur about 4 times, okay, and a value maybe between 9 and 10 would probably occur in this scenario about 1.5 times. Okay, so it tells you an idea which value is your highly likely to encounter compared to another. So in this distribution curve, okay, it will tell you that you are more going to encounter probably a value that's between 6 and 8, somewhere here, versus probably a value between 3 and 5, because 3 and 5 lies in this area. So that's just how you would interpret a distribution curve. When I'm conducting a face-to-face class, normally the exercise I would give to the participants is do a coin toss. I will give them 7 coins, and then I will ask each group to toss the coins and count number of heads and number of tails, and I would ask them to plot what they're seeing. And if the way you're tossing is that the coins is random, somewhat the distribution curve will be something like this as well. Okay, let's continue. In a process, 2 things can happen in your process. Let's say there could be what we call a drift in the central tendency. So there's what you call a sigma shift. Okay, in the example we've shown earlier, let's say customer resolution time, it might be that in the first month of operation, your average time is 5 minutes. Okay, so let's say your distribution curve would probably look something like this. It's highest near the 5-minute time. But let's say after a month or two, you got so lazy about your job, you take things slow, and now the average, let's say, of your resolution time is 6 minutes. So that's what you call a drift in the central tendency. So your new distribution curve might be something on the right here, okay, where you now have a higher resolution time, and somewhat your average is now higher than 5 minutes, or probably now in this time 6 minutes. Another way that your process can change is in terms of the variability. Okay, so it might be that you are very consistent in your first month, like the values that will take you to resolve your customer is close to each other, but maybe through time you have high variation. Okay, if you have a very high variation, your curve will be a little bit flatter, like the one here shown in the with the dotted lines. Okay, so this chart will just show you how a process output can vary through time. And in higher belts, there are ways to address process shifts like this. Okay, but for the scope of Lean Six Sigma Yellow Belt, for now we are just going to cover the different types of data. Okay, data is fundamental when you deal with a Lean Six Sigma project. So there are two ways that you can classify types of data. And the first one to describe type of data is in terms of its descriptive orientation. Okay, and descriptive orientation, the data can be a response or it can be a predictor. We'll give some examples later on. Another way to describe your type of data is in terms of the presence of gap. So there are two ways to describe a type of data. It could be a discrete or it could be continuous. And let's give examples. Okay, let's tackle first descriptive orientation. Okay, how you would describe types of data in terms of its descriptive orientation, whether it's a response or a predictor. So the only way to describe in terms of the descriptive orientation is to look back at this equation where we're probably familiar in our in algebra. Y equals f of x. It only means that y is a function of x, or y is dependent on x. That's how you interpret this formula, y equals f of x, which means if we alter x, okay, if we manipulate x, then it will have an impact on y. Okay, y is the dependent variable or the response, and x is your independent variable or your predictor. Let's give some concrete examples. So let's look at this statement. The average number of complaints is dependent on the time period, or there are more complaints during peak hours. In this example, your independent variable or your predictor is the time period. Okay, so your time period is your predictor, and your response here, or your dependent variable, is the number of complaints. Okay, so it might be that during peak hours you have lots of complaints, whereas in your non-peak hours you would have less complaints. Okay, next one. Children drinking milk are more likely to be taller. Okay, I want you to pause for now and look at that statement. Children drinking milk are more likely to be taller. What do you think is the predictor here? You can maybe type in the message, or if you can take a guess. Children drinking milk are more likely to be taller. Okay, so let's look at the responses here. Yes, So the predictor here is whether the child drinks milk or not. That is the predictor. So it's probably a yes or no. Does the child drink milk? Yes or no. That is your predictor. And your response in this case will be the height. Okay? Children drinking milk are more likely to be taller. Next one. The average number of passengers per flight is affected by the currency exchange rate. Okay? So in this case, your predictor here is the currency exchange rate, and your response will be the average number of passengers per flight. So it might be that if there's a good exchange rate, it might be that there is an increase in the number of passengers. And if the currency exchange rate is probably high, then it might be that passengers find it quite expensive. So it might be that the average number of passengers would go down. People with hypertension are more likely to be affected by COVID. What do you think is the predictor here? If you can type in the response. Okay, yes, hypertension or the presence of hypertension, that is the predictor, and susceptibility to COVID will be your response. Okay. People who studied in the urban area are more likely to perform better in the entrance exam. So here the predictor will be where the person has studied, whether it's urban or rural, and the response is the performance in an exam. By the way, these statements are hypothetical. Okay, it's probably just a hypothesis. So we have no basis whether this is true or not. And sometimes when you do a Six Sigma project, you do a hypothesis. You start first with the hypothesis and you prove it with the data. Unfortunately, for yellow belt, we won't be doing what we call statistical tests of hypothesis. This is covered in the green belt. For now, the scope of yellow belt is just for the participant to understand when there is a statement, what is the predictor and what is the response. Okay, next one. There are more sick leaves filed on Mondays versus Wednesday. Your predictor here will be the day, and your response here will be the number of sick leaves filed. And the last one is people tend to give a higher rating to a product if it is branded. Okay, what do you think? This one is a little bit difficult. What do you think is the predictor here? Okay, let's see. Okay, yeah, it's branding. Very good, it's branding. And this is actually validated in studies. I recall in the company, the first company I used to work for, there was one department that was producing iced tea. So when that iced tea was presented to consumers and it's not branded, okay, it wasn't branded, it's just there was no brand, it was just iced tea. They tasted it, and let's say the score was 7. Okay, but now it's the same iced tea, but this time they put a label to it. Okay, they put a label and they gave it to consumers again, and this time the score was higher, like it's an 8 or a 9. So it validated their hypothesis that people tend to give a higher rating to a product if it is branded. So branding actually affects perception, especially if the brand has a positive image. Okay. So I hope with these examples, you're able to distinguish a predictor from a response. Now let's look at types of data in terms of the presence of gap. Okay. So a gap, a discrete data, if there is a gap that exists between observation. Okay. Normally these are data that is counted. So for example, number of scratches in a car. Okay, number of scratches in a car is considered discrete data because you count 1 scratch, 2 scratches, 3 scratches. There is a gap between 1 and 2. There's no, you don't say there's 1.2 scratches in a car. You don't say there's 1.8 scratches in a car. It's just 1, 2, 3. Okay. And this type of data is considered discrete. You are obtained this by counting, and there is a gap between observation. When you say there's a gap between observation, there's a gap between 1 and 2. It's only 1 and 2. No in between. No 1.2, no 1.3, no 1.8. Okay? So the first type of data is discrete. The second type of data is continuous. Okay? And this one is measured by counting. Sorry, this one is obtained by measuring. Okay, an example will be length, temperature, or time. Okay, so you might want to ask, how long did it take you to do this task? Oh, it took me 10 seconds. Oh, it took me 11 seconds. But there is no gap between 10 and 11 because sometimes it might take you 10.1, or it can take you 10.12, or it can take you 10.123, and so on and so forth. So it is continuous, okay? And you can be more accurate if your measurement is able to do so, okay? In the service industry, the most common type of continuous data is always time, okay? So time is a continuous data. Okay. These might be simple topics, discrete and continuous, but it is very important because it gives you the foundation when you go to higher belt to determine what statistical test you will do. And also, if you recall earlier, there's a section in measure phase where we'll be discussing about the process capability. Process capability is a description of how good your process is. So the way you would describe your process will be dependent whether you are dealing with discrete data or continuous data. So it's very important that you are able to distinguish which data is discrete and which data is continuous. So we have covered data. Let's now go to statistics. Okay, it's the wrong one. In statistics, there are two types of statistics. There's what's called descriptive statistics and inferential statistics. The scope of yellow belt is the descriptive statistics, and the inferential statistics will be covered actually in green belt. So how is descriptive statistics different from inferential statistics? Descriptive statistics is simply concerned with collecting and describing. Okay, so the operative word here is descriptive. So it's about describing a set of data to yield meaningful information. Inferential statistics, the operative word here is inferential. You're able to make inferences or predictions. So inferential statistics is more about the analysis of the sample data and making generalizations back to the larger population. And you're drawing predictions about the population based on the data that you have. So these are probably examples of descriptive statistics. Okay, the first one, an average Czech citizen consumes about 142.4 liters of beer per year. So it describes what a typical Czech citizen would consume the amount of beer per year. Okay. Next one, an example of descriptive statistics. The median age of a female marrying in the Philippines is 25.6 years. Okay, so you are more likely to find somewhere between 25 and 26 female to be marrying around that time. Okay. Another descriptive statistics, the three-point shooting percentage of Stephen Curry is 43.3%. Okay, so it describes about the data. Here are some examples of inferential statistics. So it could be in form of a question, or normally in an inferential statistics, you have a hypothesis and you try to validate that by gathering data. So the first one is, will a male Filipino voter more likely choose a male candidate? Okay. So it tells you about you're making an inference, okay, or the likelihood of a voter to choose a male voter to choose a male candidate. So you are making an inference based on the available data that you have. The second one, is there a correlation between height and career advancement? So here you're making a hypothesis that does it follow that if a person has, is taller, does it mean that in terms of career advancement, it's probably higher? Okay. So to answer that, you will need inferential statistics. Okay. Third one is a statement. The level of happiness among individuals from Finland tends to be higher compared to individuals from Japan. So here you're making an inference that if you choose a random person from Finland and a random person from Japan, this statement says that you are more likely to find that the level of happiness of this random person from Finland to be higher than the individual from Japan. Okay, so these are inferential statistics. We won't be doing statistical tests of hypothesis in yellow belt, but it is important as a yellow belter that you know the difference between descriptive statistics and inferential statistics. Okay. And the next section of measure phase, which is next week, we will cover some of the charts that are used for descriptive statistics. Okay, so descriptive statistics will be part of the scope of yellow belt. Okay, we will cover next week the graphical presentation. Okay, we will cover box plot, histogram, Pareto chart, scatter plot, and run chart. Okay, and then we will discuss about numerical measures, location and dispersion, and that's the focus for the remainder of this session, the numerical measures. We will cover first numerical measures in terms of location. And I bet that a lot of you are already familiar with the concepts here, the measure of location, of central tendency. So there are three common measures of location for central tendency. The first one is the mean, which is just the arithmetic average of all observations. Okay, so everyone here, I would assume, knows how to get the average. Okay, you just add all and then you divide the number of observations. If you are using Excel, you use the formula average and then you highlight the cells that you would want to average. Median is another measure of location. It's the middle value in a ranked data. Okay, so what it means is that you arrange the number from highest to lowest and the middle value is counted as the median. Okay, and using Excel, you can use the formula median and then you highlight the values that you would like to evaluate. And the last measure of location is the mode. And this is the most frequently occurring value in a sample. Okay? And mode can be computed in Excel equals mode and then the values that you would want to evaluate. However, the limitation in Excel, because a group of data can have more than one mode. It is possible if the value you have two equal frequently occurring value, then you can have two modes. But in Excel, the Excel will only return the lowest value that would be counted. Okay, so that's the only limitation for mode. And for practical purposes, normally we are dealing more on mean and median. Okay. So you might be asking, when is median useful? Okay, because we already have the mean, which is just the average. So why do we still have the concept of the median? Okay, if you recall, median is the middle value when you arrange it from highest to lowest. Okay, so this example will probably drive home the point when median is useful. So imagine there is a taxi driver Okay, in New York City, there's a taxi driver. And let's say you are a banker and you took this taxi. Okay, so it was rush hour, took this taxi. And suddenly you had another passenger. Okay, he requested to join you in the taxi. So right now there are 3 of you in the taxi. So this guy here called Stephen Curry, there's a taxi driver, and then there's you. And now the question is, suddenly someone asks the question, what is the average salary of the people inside the taxi cab? Okay, so what is the average salary of the people in the taxi cab? So let's look at their annual salary. So a typical taxi driver would earn 26,000 US dollars per year. A typical banker would earn 100,000 US dollars per year. And this guy, Stephen Curry, earns 48 million US dollars a year. So if you're going to answer this as in terms of the mean, that the average salary of the people in the car is roughly, what is that? Maybe 12. My math now is 16. So it appears that the average salary of the people in the car is 16 million per year. But that's far from reality because, 2 persons here, they're just in the range of thousands. So in this case, average is not a good measure. Okay? What would reflect the reality will be when you ask, what is the median salary of the people in the car? So in this case, the median salary, the middle value here will be 100,000. This is the median salary. So this is probably closer to truth because the taxi driver is closer to 100,000. So it probably is more correct for 2 of the individuals. So the median, okay, when you have sets of data, the advantage of the median is that it is not affected by extreme values. Okay, so median is useful when your data has extreme values. In this case, the extreme value here was the salary of Stephen Curry. That if you use the mean to calculate for the average salary, it can be misleading because of this extreme value that pulled the average. Okay, so always remember that when is median useful? You only you use median instead of the mean if your data set has extreme values. But most of the time, I think for yellow belt, we will be dealing with values that are not really extreme. So most of the time, probably just using mean. Okay, let's continue on. And then there's another concept of quartile. Oh, there's a question. Let's see. Yeah, extreme outlier. Correct. Another concept of location is what you call the quartile. There's a quartile 1, quartile 2, quartile 3. It's basically you just arrange the data from highest to lowest. Quartile 1 is the point wherein 25% of the values would fall below it. Quartile 2 is actually also called the median. It's where 50% of the value would fall. Okay. And quartile 3 is the value wherein 75% of the value will fall below it. In the graphical representation, we will encounter again the concept of the quartile, and you'll probably appreciate it more, how quartiles can give you a better appreciation of the dispersion or how varied your data is. Okay. So just remember, quartile 1 is where 25% will fall below. Quartile 2 is where 50% will fall below. Quartile 3 is where 75% will fall below. So the mean, median, mode, and the quartiles are measures of location. We now go to the measures of dispersion, okay, or how varied the data is. So the first measure of this dispersion is the range, which is just you get the highest value and the lowest value. That is the range. Okay. And then the other measure of this dispersion lumped together is variance and standard deviation. Okay. There's the formula here, but fortunately for us in Excel, there's this formula. Okay, so range. Oh, sorry, I haven't updated this one. This is not average. The difference will be the minimum. So this is wrong. The one on range. I have to update this chart. Let me just put here. Okay. Sorry, this is wrong. In Excel, yes, correct, Jonas. In Excel, there is no value or range, but what you can do is max. Okay, put max. It's hard. Minus minimum. Okay, that's how you would get the range in Excel. It's the maximum value minus the minimum value. And standard deviation is the average deviation of data from the mean. There is a formula where the hard way is to get first the average, then you subtract the average from each individual value, and then you square it, and then you divide it by the total value, then square root. It's a bit complicated, but fortunately, Excel now has the standard formula called standard deviation. These are the typical measures of variation, range and standard deviation. The advantage of range, okay, the advantage of range is very simple. Okay, you just get the highest value and the lowest value, and you get to solve for the range. The disadvantage of the range, though, is that it only takes into account two values, okay, the highest and the lowest. It doesn't take into account all the other values in between. Okay, so that's the disadvantage of the range, and that's why for measures of variation, the most common term that's computed is actually the standard deviation. Standard deviation is a measure of how varied your data is. Okay, if the standard deviation is high, it means that your data has high variability. If the standard deviation is low, it means that your data has low variability. It's very, very consistent. Okay, I guess that's it for this section. We've covered a variation, and I guess the best way really is to have a quick practice before we go to the Q&A piece. So right now, wait, let me just see this chart. Okay. Right now, I'm showing to you the average number of passengers leaving and exit per trip, okay, at LaGuardia Station from 4 to 5 p.m. Okay. The first question is, what type of data this one is? Is it continuous or discrete? They're talking here of average number of passengers. This is discrete, yes, because you count the number of passengers. You don't have 1.2 passengers. You don't have 1.5 passengers. Okay. Next, the question is, what is the average number of passengers per exit? I think this one is quite easy. You can, if you're able to copy this, you just get the average for that one. And then what's the overall average? You can just copy this in Excel and then use that one. I'll probably give this to you as an assignment. Okay, you'll be given a copy of the handout, and I'll probably just put as well in Kahoot. Try to solve first on your own how to get for the standard deviation of the per exit. Okay, that's it for now for the first section of the measure phase. I'm gonna we will continue the discussion for part 2 next week. So I'm gonna pause now the recording for now so that we can proceed to the Q&A. Okay, how do I pause?